Hello and welcome. Projectile motion lesson number 2. I went through the first question a couple of days ago. So this is now again from my book, question 2. I hope it's visible in the video. If not, I will be reading it. Just some general points. Anything to do with mechanics. First of all, do not read from beginning to end, trying to absorb. The first thing you should do is identify the topic. What topic is it? And then decide, of course, on the particulars of this type of question. So once we read this very quickly, we said, okay, it's a projectile. The next thing, is it ground to ground, or is it from a height, let's say the top of a cliff, projection? So here, project from point O, blah blah blah, no reading, reaching a greatest height, blah blah blah, before it lands on the ground at the point P. So it's a ground to ground projection. So for something like this, what I will be doing is a standard diagram. It's an XY plane diagram, which looks something like this. Okay, so this is my XY plane, Y and X somewhere here. This is the path of the projectile, we can think of it as a golf ball, so also known as the trajectory. So the particle is projected from a point O, conveniently, that's the origin, on level horizontal ground with speed 45.5 meters per second. No units in my diagram. This is my projection speed, 45.5, tangential to the path. At an angle beta to the horizontal, so the angle beta is here to the horizontal. What do I know about this angle? Does it tell me how big it is? It's telling me the tan of this particular angle. So it's as good as telling me the angle. So I'm going to put this extra information on the side here. The tan of beta is 12/5. Modern calculators these days can compute a lot of things. So strictly speaking, this triangle is not really required, but I still advise my students to use it. So that's my angle beta. Tan 12/5, so that is 12 and 5 here, of course not to scale. And using Pythagoras, you'll find that the missing side is in fact 13. And therefore, from this bits of information here, we have that the sine of beta and the cos of beta equal and equal. The sine is 12 divided by 13 in exact form, and the cos is of course 5/13. So let's put this information in a box. And let's read. Particles projected, level horizontal ground, speed 45.5, angle beta with its particulars. The particle is moving freely under gravity, reaching a greatest height of h meters. So h meters is not the point here, it's actually the height. So that's h there. And this point, I think they're calling where it lands P. So I'm going to call this point Q. So Q is the position of the particle, the golf ball, when it's at its highest. And then it's asking us for all sorts of things. So I'm going to complete the picture. What are the bits I'm missing from the picture? The acceleration is vertically down, gravity, G, 9.8 downwards. And I always put in this kind of pictures this initial velocity configuration. What does that mean? Well, I've got a 45.5 initial velocity of projection or speed of projection at some angle, and I'm going to write these components here. So this is now the vertical component and the horizontal component of this 45.5. This angle here is beta, so it's like resolving forces. So that's going to be 45.5, and the angles on this side, so that's the cos of beta, and 45.5, the other components, of course, the sine. And of course, we have the sine of beta and the cos of beta. I'm going to use my calculator. So 45.5 times the cos, which is 5 divided by 13. This gives me an answer of 17.5. So in fact, this is 17.5 meters per second. And the other one, 45.5 times the sine, which is 12/13, times 12 divided by 13 is 42. So in fact, I can ignore these quantities here and I can just work with 42 and 17.5 5. Okay, so I've got all my information done, and now I can look at the question and say, okay, what do you want now? Just a reminder what these things mean. This is constant. The speed to the right, the horizontal component of this velocity, 17.5, is constant to the right. Never change, doesn't speed up and slow down. While this is only at the moment of projection. As it's moving, this is getting less and less and less and less until it goes 0 here, 0 vertical velocity, and then it will pick up speed going downwards, and by the time it's back at P, it will have exactly the same speed down, 42, but of course there'll be a negative sign there. Okay, first thing that the question is asking, find the flight time of the particle. In other words, how long does it take to complete this journey? We're going to get this from the vertical velocity, sorry, not vertical velocity, from the vertical motion rather, I'm saying stupid things, because if I knew, for example, how long this is, from O to P, how many meters, I can work it out from there, but I have no information, so I'm going to look at the vertical. So I'm looking vertically, the entire journey, so I'm going to put vertically O to Q to P. So that's the journey that I'm looking at, and I'm filling in now my usual quantities, my kinematic quantities, UA, S, T, and V. And these are my constants at the top, and these are my variables. So I'm projecting upwards with a speed U, which is 42. Remember, that's the initial vertical speed, subject to an acceleration of minus 9.8. That's the G there, minus because pointing downwards. What identifies this point P as far as the vertical motion is concerned? The answer is 0 displacement. When the displacement, the vertical displacement is 0, what is the time that goes with it? Let's talk about displacement very quickly. The displacement when the particle is here from the ground is 1 meter, 2 meters, 3 meters. I don't know how high is this point. Let's say 10 meters, 15 meters, 20 meters. And then when it's here, it's 19 meters. It's 19 meters from the ground. 18, 17, 16. And by the time it's back at P, it has 0 displacement relative to the ground. That's the positive. Imagine that was a cliff. So imagine that wasn't there. So it was like a cliff going down like this. And the particle was to continue going down. The displacement down here might be -2. It's below this level, -4, -5, and so on. Of course, here we have the ground, so we can continue with our problem. So what equation do we use for this? U, A, S, and T is, of course, S is equal to UT plus a half AT squared. 0 is equal to 42T plus a half minus 9.8 T squared. Let's tidy this up a little bit. 42T minus 4.9 T squared, factorized by common factor at T. So it's going to give us 42 minus 4.9T. And of course, we're going to get two solutions. Either T must be 0 from this bit here. Is it a valid solution? Yes, it is, but it's not the flight time, because of course, all it's telling us is, you know what, when the time is 0, you have 0 displacement. Of course, thank you very much. I knew that. I'm still at O. But it's the other number that's going to come from the bracket. That's going to give us the answer. And I'm going to use a calculator for that. And it is 42 divided by 4.9. And this gives me an answer of 60/7, which is approximately 8.57 seconds. So that's the flight time. I will leave it in exact form as well, just in case I need it for anything else. So find the flight time of the particle, done. That's part A. Okay, part B, hence determine the distance OP, in other words, how far does it land, and what is the value of H, and what's the value of H, in other words, what's the greatest height that it reaches. These are doable very easily now. And there's part B. First of all, the horizontal distance OP. We're going to use the, on the first lecture I did do a method that has suvat in it, which is a little bit bizarre. I'm not going to do it. Horizontally, there's no acceleration. It's moving at constant speed. So the distance in the horizontal, actually I'm going to write distance horizontally. because it does, it's referring to the horizontal distance. Horizontally is equal to speed times time in speed marks. So the distance OP, which is the horizontal distance, can be found by multiplying the horizontal component of the speed, which never changes, is constant, 17.5, that's, we wrote it there in the beginning, times how long it will take to get there. Well, the ball will be moving for 60/7 of a second, so it's for 8 seconds. So the answer to this particular one, we're going to put into a calculator, 17.5 times the 60/7, it will give us 150 meters. So that's this distance here. Okay, and what is the value of h? This, of course, is a vertical calculation. So we're going to look vertically, O to Q. So the journey that I'm looking, and this kinematic quantity is referred to, is for O to Q. O, U, A, S, T, and V. Okay, I'm projecting upwards with a speed of 42. That's my initial vertical. Subject to an acceleration, vertical, of -9.8. What identifies this point there is now two different quantities. I can take my pick because I worked out the flight time as well. What I know, first of all, up here I have 0 vertical velocity. So I can put 0 for the V. But I also know that since the whole flight time is 60/7, found here, then it will take exactly half that time, so 30/7, to reach the maximum. So from this, I can take the easiest equation to find my S. I can use whatever I want in there. The easiest one, you can use V squared is equal to U squared plus 2AS. You can use S is equal to UT plus 1/2 AT squared. You can even use this one, which is not often used. S is the average of the two velocities multiplied by the time. And I think it's probably easier because if we have 42 plus 0 divided by 2 times the flight time, which is 30/7. So that's in fact 21 times 30/7, which we can even do without a calculator. The 7 will cancel out to a 3, so we're going to get 90 meters. But you can use whatever equation you want now, having all these bits of information in there. So h, in other words, that's your h, of course, because the question says find the value of h, which they defined earlier on in the question. Determine the distance OP, 150 meters. The value of h is 90 meters. Lastly, determine the speed of the particle 4 seconds after leaving O. In other words, 4 seconds after it got projected. So, first of all, just to get our head around this, where is the particle at that point? Is it on the way up? Is it on the way down? Since the total flight time is 8.57, it will be just over 4 seconds to reach the maximum. So it's probably just before it hits the maximum. So it's somewhere here, let's say. Okay. So that's when the time is 4 seconds. Let's call this OPQ. Let's say this position R. We want to know the speed of the particle. Speed. What is speed? Speed is, of course, when we're moving in 2 dimensions, like in a projectile motion, is the resultant of the vertical and the horizontal component. For example, I'm just going to put a little diagram. If I'm moving with, of course, a constant speed of 17.5, because this will never change, and at that point I'm moving upwards momentarily at that instant with a speed of 10, then my overall speed, okay, will be 10 squared plus 17.5 all squared, square root by Pythagoras, because of course this bit here will also be 10. So 17.5 here, all squared, and so on. Okay, so what we need to do, let's draw this picture now for ourselves. We can draw it actually here as well as on the side, so we can be happy what we're doing. We actually are trying to find this speed here, which of course is a combination of this component. Let me just move the R from there to the left, and this component here, which of course we know what that is. This never changes, is 17.5. We just need to find that and then we're done. So basically we'll have 17.5, and the question is now, what is this quantity here? How are we going to find? So that's the speed here. It's the resultant. Okay, we need the vertical velocity. This is a velocity now, vertical. So we're going to look at the journey. So vertically from O to the point which are labeled as R. U, A, that's my constants, S, T, and V. Let's put all our equals to see what we know about this particular journey. We're projecting there with a speed of 42 upwards, subject to an acceleration of minus 9.8 downwards. What identifies this point is, of course, the fact that they told us determine the speed 4 seconds after leaving O, and therefore there the time is 4. And what are we after? Are we after how high it is? No, we're after what's the velocity at this point. So we need the V there. What equation we need for that is very simple. It's actually the easiest one. V is equal to U plus AT. V is equal to 42 minus 9.8 times 4. V is equal to 42 minus, I don't want to use a calculator for that, 0.2 times 39.2, I hope. And that is a 2.8. So a tiny little bit of velocity, because it's close to reach zero velocity here, so it's just a little bit before it reaches the highest point. So 2.8 here, and therefore we're done. The speed from this diagram, or this type of diagrams, is a resultant. It's always Pythagoras when you're combining vectors like this. 2.8 squared plus 17.5 squared square rooted, and definitely calculator for this. I'm not gonna be attempting this, of course, in my head. So when we do that, and a sensible accuracy in the absence of instructions, 3 significant figures is good enough. I'll make it 17.7, or you can even give it an answer of 17. I should put really approximately equal 17.72 meters a second. That is the speed of the particle 4 seconds after leaving O. I hope you follow projectiles. Projectiles can be tricky. They're not the most straightforward topic. It will take a lot of work on your part, but I hope things click in. I'm signing out.